So, what do we know about singularities? So, if f has a pole at z0, then that exactly means we define it to be this, that f of z has 0 at z0, i.e. if it has a 0 at z0, 1 over f of z is equal to z minus z0 to some n, and then some holomorphic function g, where g of z0 is not equal to 0. And then we unwrap that, and then we get, so f of z is equal to z minus z0 to the minus n, g of z to the minus 1. And then, since g is a nice holomorphic function, which is non-zero, we can just expand it, and then we find out that it has some expansion like this, k equals 1 up to n a to the minus k z minus z0 to the minus k, and then some function, let's say h, which is holomorphic. Right? And so this h thing, which is holomorphic, we can do a Taylor expansion of it. So what we have is implicitly some kind of more general expansion than a Taylor series, because we are expanding to the negative powers of z minus z0, right? And that's a very useful thing. We've used that lots of times. It turns out, however, that we can actually expand even when we don't have a pole. We can expand, and we'll have a series which will have a negative powers or sum of negative powers, and we'll have that holding true inside some annulus, where we can fit the annulus inside the domain where it's holomorphic, and that is called Laurent series. Okay, so more generally, we can do this. We can expand into negative powers, negative even when we don't have a pole. And how does this work? Well, this is our theorem. So suppose we have that f is holomorphic on omega, and we have that. So I'll define this in a second. We have that annulus, say 0, 1 is contained within omega. Then we have that f of z is equal to the sum from k equals minus infinity to infinity of ak z minus z0 to the k, where these ak are 1 over 2 pi I. C is going to be any closed curve inside this annulus, C, and we're going to have f of zeta minus z0 to the k plus 1 the zeta. Okay, so what's the picture? The picture is that we can have a holomorphic function, and there can be some holes inside our domain, like this, right? Or they could just have some singularities inside, right? And if we fit some annulus inside our domain like this, right? Then we can have a power series expansion holding true inside this annulus, given by these coefficients. So, for example, if we did it around the singularity, then we could just have whatever punctured ball we could fit inside the domain, right? And then this thing still holds true. And if you think about that case, if the singularity is just a pole, then we already know this because this is what this has already given us, right? Yeah. So the real purpose of this, the real use of this is actually, well, the real purpose, well, what the new thing that this thing will actually give us is the ability to do an expansion around an isolated singularity, which is not a pole, i.e. is actually an essential singularity. Yeah. And if it's an essential singularity, then that is equivalent to the expansion of the negative powers of z minus z0 being infinite. So when we have the expansion of the negative powers being finite, then it's just a pole, right? And it's easy to see that's necessary and sufficient, right? However, we do have situations where there's an essential singularity, right? And we might want to expand around that inside some annulus. And we can actually do this. So this is essentially the new thing that this gives us, that we have the ability to do an expansion around an essential singularity. Because if it's removable singularity, then it's just a Taylor series. If it's a pole, then it's this thing, which is quite easy, right? So this theorem is main new thing is just for that context. However, it's kind of neat that we can do this nevertheless. We can actually expand around an essential singularity and have a non-trivial new expansion that holds true inside whatever annulus we can fit inside our domain. Okay, that's what Laurent series is about. Cool. All right. Let me erase the board. Are you all clear on the statement and everything I've said so far? Yeah? Everybody happy? Give me a thumbs up if you are. Okay, cool. Okay, so how do we prove this? All right, so A of Z0, R0, R1 is this thing. It's just a ball of radius R1 at Z0. Take away the closed ball of radius R0 around Z0, right? So it's this thing like this. Where this is R0, and this thing here is R1. Okay, just as you'd expect. Okay, so we're assuming that this thing is contained within our region omega. Okay, and we're going to take two circles which are close to either the inside or the outside. So let's take a circle C1, which is close to the, let me change color to red. Let's take a circle C1, which is close to this outer boundary, like this. And obviously we're going to make it arbitrarily close. And then let's take a circle C0, which is very close to the inner boundary, like this. Okay. So take circles. C0 and C1 is shown. And suppose Z is inside C1 and outside C0. Okay, so we pick some arbitrary Z, whatever, here. and this thing is Z0 here at the center. Then, the first claim that we actually have that f of z is 1 over 2 pi I, the integral around the larger circle, f of zeta, zeta minus z0, d zeta, minus 1 over 2 pi I, the integral around the inner circle. All right, tell me why we claim that. Why is that true? Look at this picture here. Why is that true? Okay, so if I did that, if I made a corridor like this, how does that help me? Agreed, but why is it the case that the integral of the outer circle minus the integral of the inner circle is equal to f of z? Let me write some stuff down. So let's call this thing camera of delta, right? So we know that the limit as delta goes to 0 of the integral of camera of delta of this thing is exactly equal to what you say, the outer circle minus the inner circle. Yeah. So why would this thing be equal to f of z? Cauchy integral formula, right? So long as this gamma delta and its interior is inside what I previously said was a delta good domain, but now we just need to know that it's inside our simply connected domain, and of course it is, because it is simply connected itself, being the interior of a closed curve. So yes, this thing is something we can apply Cauchy's integral formula to. So, and by Cauchy's integral formula, we have that f of z equals 1 over 2 pi I, the integral of this thing for any choice of delta of f of zeta, zeta minus z d zeta, like this. And that just follows because if we just take a ball around zeta, then that's the thing that we proved for, right, for a very small ball. And then we can just deform this curve onto the ball with this kind of contour integral with the corridor stuff. That's stuff we've done lots of times, right? Yeah, cool. So we can do that. We can break this up into this integral around the outer circle minus the integral around the inner circle. Okay, now let's look at the integral around the outer circle. So notice that when we look at the integral around the outer circle, zeta minus z, the zeta, then we can do this trick. We can go, okay, this is of zeta, and then let's do zeta minus z0, and then let's write z0 minus z, like this, right? And zeta, when it's on the outer circle here, let's change color. When zeta is on the outer circle, then this quantity, zeta minus z0, has this radius here, which is like almost like R1. It's just a bit smaller than R1, right? whereas z minus z0, right, is something much smaller. Yeah, as you can see from this picture. Yeah, so we can factor out this zeta minus z0 from the bottom line here, and then we get this f of zeta minus z0, and then we're going to have 1 plus z0 minus z over zeta minus z0 like this, right? And let's write this as minus minus, which we can do, right? So if I swap the z0 and the z, then I can write this as minus this thing minus z0 like this. Yeah? Yeah? Cool. And then what is this thing? Well, for every choice of zeta, this thing is a complex number strictly smaller than 1, right? This thing here is a complex number strictly smaller than 1, just by what I just said, that this distance is a lot smaller than zeta minus z0, no matter what zeta we have on this outer circle. Yeah? Cool. All right, and then we do this Taylor expansion. This is exactly how we proved. So again, then we do this geometric series expansion. This is exactly how we proved the Taylor series before. Right, so then this is equal to C1 f of zeta minus z0, and then we have the sum from k equals 0 to infinity, z minus z0, oops, over zeta minus z0 to the power k d zeta. Yeah? Cool. And what we'd like to do is to swap the sum and the integral, right? And that's what we did quite carefully when we did this proof, right? Yeah. But it turns out we can do this because this series will converge uniformly. Start that again. The partial sums of this series will converge uniformly to the series for any zeta around the outer circle because it's dominated by this geometric series given by the absolute value of this expression here. Yeah? Yeah? That's what we did before. So look back on your notes for how we argued this. Recall we can swap limits and integrals whenever we have uniform convergence, and the partial sums of this expression converge uniformly to its limit for any zeta on the ball. Right? And we can give an explicit error bound of how far away the nth partial sum is to the actual series. Do you have some memory of this? Is this coming back a little bit? Yeah? Cool. So if we swap the sum and the integral, what do we get? We get the sum from k equals 0 to infinity, and we are going to have z minus z0 to the k, integral around this closed ball like this, and then we're going to have f of zeta over zeta minus z0 to the k plus 1, the zeta, right? Yeah. And then we divide everything by 1 over 2 pi I, because it's inside this thing, right? And then we'll have these coefficients divided by 1 over 2 pi I, and that's exactly the Taylor coefficients that we know, right? Yeah. And we also know that this is equal to the kth derivative of f at z0 divided by k factorial. Right? That's exactly how we prove Taylor series. Yeah. So the contribution from the outer circle gives us the Taylor series part. Right? So this part right here is equal to the kth derivative at z0 when we divide by 1 over 2 pi times 2 over k plus 1 factorial over k factorial times 2 pi I. right? Because we haven't divided through by the 2 pi I yet. Yeah? So that's exactly what we expect and what we want. So this is giving us the Taylor part of the expansion. Of expansion. Cool. So now we're going to think about this other term, this minus 1 over 2 pi I around the smaller circle. Okay, and as you can expect, that's going to give us the negative indices, and that's what we're going to see. Okay, so let's draw the picture again. So we have our annulus, not a very good annulus, and we have our 2 balls, or 2 circles. This one was the larger one, the C1. And this was the smaller one, the C0. Yeah? And we had some Z inside here. Cool. So we had our representation that f of z was 1 over 2 pi I, the integral around the larger circle, f of zeta minus z d zeta minus the integral around the smaller circle, f of zeta minus z d zeta, which just followed from Cauchy's integral formula and doing this corridor going down to 0 stuff. And now we're interested in this expression right here, because we know that the other one just produced the Taylor series, right? So if we look at this expression right here, so consider the integral around this smaller ball, f of zeta minus z d zeta. Again, we're going to break this up using z0, so c0. Let's put a minus sign here. Let's put a minus, because this minus sign is here. And what do we have? Let's write zeta minus z0 plus z0 minus z, like this. Yeah. And now let's think carefully about the size of these relative terms, because we are here, right? Zeta is here. This is z0 here in the center, right? So this distance here is very close to r0, and it's definitely less than this thing. Oh, this is so messy. Let me do that again. So this is the central point here. This is z0, right? So this distance here is definitely bigger than z0 minus zeta for any zeta going around. Yeah? As you can just see. Yeah? Because look, this distance here is definitely bigger than this distance here, because this thing is outside of the circle of radius, whatever the radius of it. Okay. All right. Let me get a bigger picture on the board then. Okay, let's do a bigger picture. So this is the outer circle. This is the inner circle. Yeah? This thing is z0 right here. Yeah? Z is somewhere between these two circles. Yeah? And zeta lives here, entering around the inner circle, right? So this is circle C0, and this is circle C1. Yeah? And then zeta is here. Yeah? So the absolute value of z0 minus zeta is always the radius of the inner circle, whereas the absolute value of z minus z0 is something definitely bigger. Yeah? Cool. So notice that this time we have that mod z minus z0 is definitely bigger than z0, zeta minus z0. Oops. and this is the important point, for any zeta on the circle, because we need it for any zeta because we're going to ultimately pass the limit through the sums. So that again, we're going to take the sum through the integrals, we're going to pass the limit through the integrals, and we need this geometric series we're going to get to actually converge, right? Absolutely, to control the error. So this is true for any zeta inside this circle C0. Yeah? Cool. So from this expression right here, from star, we want to rewrite this, and we're going to ultimately use a geometric series, right? But we're going to have to put this in the form of 1 plus or minus something, where that something has got absolute value less than 1. Yeah? Yeah? And this time we're going to make the smart choice using this inequality, right? So we need this thing to be the thing which is on top, and we divide through by this thing in order to have something strictly less than 1. Yeah? So that means we're going to factor out this thing this time. Yeah? So this thing is equal to minus this thing, and let's factor out this z minus z0, and then we're going to have 1, messy 1, do it again, and have 1. So we factor out z minus z0, this is 1, and then this thing is going to be zeta minus z0 over, sorry, this is z0 minus z, right? That is what I factored out from here. So this will be zeta minus z0 over z0 minus z, like this. Yeah? The zeta. So all I've done is factor out this z0 minus z from this. So this thing becomes 1, and this thing becomes zeta minus z0 over z0 minus z, like this. Yeah? With me, people? Cool. All right. So this thing is strictly less than 1. So again, we expand it as a geometric series. But before we do this, we want to make it neater, because we want to flip this around, so to make it a minus sign. And let's also flip this thing around so that we have z minus z0. So let's do that first before we do the expansion. So this, oops, and I should say we're entering around z0. So then we're going to have f of zeta, and on the bottom we are going to have z minus z0, flipping this around and getting rid of the minus sign. So this minus sign goes to flipping this thing around, and then this thing we have 1 minus, and let's have, oops, zeta minus z0 over flipping now this thing around, z minus z0, like this. Yeah? Like this. And this thing is integrated with respect to zeta. Yeah? Cool. And now we can do the geometric series expansion. So this is the integral 0, f of zeta, z minus z0. And what is this thing going to be? It's going to be the sum from k is equal to 0 to infinity of zeta minus z0, z minus z0 to the power k, like this, d zeta, right? And let's put all that stuff all together. So what are we going to have? We are going to have integral this thing. Let's pull out the powers of z minus z0. So we're going to have z minus z0 to the power of minus k minus 1, right? From this thing and from this thing. Yeah? And then we have f of zeta, and then it's going to be zeta minus z0 to the k, like this, right? Let's get rid of this one. And then this thing is integrated with respect to z. Oh, I forgot the summation signs. Yeah. So let's do that again, this thing. And then we have the sum from k equals 0 to infinity, and then this whole expression like this. Yeah? Cool. All right. Now, the point is that this sum of terms, again, is uniformly going to converge start that again. The partial sum of this stuff is uniformly going to converge to its limit. Because again, this is a geometric series where the absolute value of the terms is strictly less than 1 for any zeta inside this thing, right? So exactly the same argument which we use to prove the existence of a Taylor series allows us to swap the partial sum, start again, allows us to swap the sum with the integral because the partial sum tends uniformly to the actual sum. So it's an identical argument, just using the fact that if we take the tail end of this, say the sum from k is equal to m to infinity, and the absolute value of this expression right here, we can show it is less than some number less than 1 to the power m over 1 minus whatever. Yeah? Does that seem familiar? Yeah? So that means that we have the right to swap the summation and the integral. And when we do this, then we pull out this entire thing, which is not being integrated, right? So then we have the sum from k equals 0 to infinity of z minus z0 to the minus k minus 1. And then this integral like this, the integral around c0 of f of zeta minus z0 to the k d zeta. Yeah? Cool. All right, let's change the summation. Now let's start with k equals 1. Because if we start with k equals 1, then this thing now becomes k, and this thing now becomes k minus 1. Yeah. So right now we're starting with 0. So okay, let me write this like this. This is minus k plus 1, like this. Yeah. So if instead of starting with k equals 0, so the first term here is 1, we start with k equals 1. Yeah. Then this guy here would have to be k minus 1, because for the first time we're going to get 0, and this thing would be k. Yeah? So I claim that this is the same as the sum from k equals 1 to infinity of z minus z0 to the minus k, and then this integral like this to the k minus 1, just like this. Cool. And now let's not take the sum from k equals 1 to infinity. Let's take the sum from minus 1 to minus infinity. Okay? So then this is now, so if I was being really formal, I would change from k to something else, but I'm going to run out of letters and I don't want to do it. So I'm just going to call it k all the time. So k to minus 1 to minus infinity. And then this term now becomes z minus z0 to the k. And then this thing, this k is going to be replaced by minus k, right? Oops. So we're going to have minus k minus 1 d zeta. Yeah? Cool. I'm going to get rid of this picture and then put details in here. Okay, so putting details inside here, so let's call this thing star. What is this thing? Well, this thing is actually exactly what we want, right? So this expression is exactly the same expression we claimed we had before, right? So well, I mean, there's no point rewriting that because I'm just going to write exactly the same thing. Let me instead go from here. So recall that we are supposed to divide by 1 over 2 pi I everything, right? So when we consider minus 1 over 2 pi I of this little circle S0 of this thing, yeah, then this expansion we have here means that this is the sum from k is equal to minus 1 to infinity of z minus z0 to the k, and then ak, where AK is the same expression that we had before. It's 1 over 2 pi I. And now we're integrating over this circle C0, but as I'm about to point out, we can integrate over any closed curve inside the annulus. But let's just write it like this for the time being. F of zeta over zeta minus Z0 to the k plus 1 like this. And this is exactly the same expression we had for the Taylor series, right? And this is what we claimed was true for any coefficient from minus infinity to infinity. Yeah. And then the final thing to point out is that even though this is around the circle C0, which was this inner circle, and all of this stuff is inside an annulus, where we have things are analytic, say holomorphic, so to use that word more, then we can, instead of integrating around C0, we can integrate around any closed curve inside the annulus and replace this expression by that expression because the deformation of curves, because we can do this corridor connecting the inner circle to whatever closed curve we want. And then inside this thing, we have something which is holomorphic inside this closed curve and on its boundary, and then there exists a primitive, and then the whole thing is equal to 0. So we can deform this inner circle to any other curve. So these coefficients, you don't have to take the inner circle, the outer circle, any closed curve will give you this thing. Yeah? Cool. All right, so that's it. That's giving us, so this gives the claim. And this can be done, of course, on any annulus you fit inside your domain. And if you fit your annulus inside a domain where it's actually holomorphic inside the ball, which is the outer side of the annulus, all that means is that all these negative powers will just vanish. All these negative powers will just vanish, as you can see from this expression, because if F is holomorphic, then since this is a negative power, if you have a negative power here, then this thing will just be 0, just because it's an analytic function in a closed ball, right? Yeah? So this theorem holds true as stated, no matter what annulus you stick inside your domain, but if the annulus is such that in the inner circle of the annulus it's just holomorphic or has removable singularity, then it just gives you back Taylor series.